Assalamu alaikum. In today's lecture, we're going to discuss a very important topic in operating system. How can we actually preserve the consistency, coherence, and correctness of our system while we are running multiple processes that share multiple resources, including data? In this chapter, we will discuss a few mechanisms, techniques we use to allow processes that share resources within the operating system, that includes data, files, and shared variables, to deal with these shared variables, files, data structures in a manner that will always guarantee that the values of these shared items are always correct and consistent. We will look through a very brief background, then we will define what the problem is, and we will explore few solutions of the problem. The main objectives of this chapter is to present to you the concept of process synchronization and to let you understand what is the problem with having a critical section of any process code that needs special considerations when executed, and how can we solve this either with pure software solutions or with the help of the hardware. You will also examine several several problems, classic problems based on the concept of synchronization. And you might explore some examples of synchronization problems. As we've said before, operating systems evolved so that multiple processes are presented in the main memory, running concurrently or parallel. That means on a single CPU or on multiple CPUs, using all the resources of the system. This is a crucial part of modern operating systems that actually provides better utilization for the resources, more user satisfaction, and it actually addresses many objectives of the design objectives of the operating system. But it also creates problems. That means it gives processes concurrent access to data entities that they share. And this might result in data inconsistencies and incorrectness, as we shall see. It's up to us as designers to come with solutions that will maintain the consistency and correctness of the data, the shared data, while different processes are actually still executing concurrently. Let us consider the problem we have discussed briefly in the past chapter when we addressed a consumer producer that's sharing a buffer where a process produces data items in the buffer and the other process is consuming data item from the same buffer. When the producer produced a new item, it will declare that with increasing the value of a common variable, let us call it counter, by 1. That means a new item is entered into the buffer. While when the consumer consumes an item, reads an item, it will declare that this item has already been read or consumed by decreasing the value of counter. The importance of counter is the producer can only produce number of items as long as I have a bounded buffer that equals the size of the buffer. And the consumer cannot consume items if the buffer is empty. So they both use use counter to understand how full or how empty the buffer is. Initially, counter is 0, and every produced item it will be increased by 1. And with every consumed item, it will be decreased by 1. So, if we look at this code, the producer code, if the producer will examine the value of counter. If the value of counter equals the value of the buffer size, it will do nothing. If there is an empty slot, it will produce a new item, write a new item, store it in the buffer, increase the value of counter by 1. While the consumer, on the other hand, will come and examine the value of counter. If the value of counter was 0, that means nothing is written into the buffer, it will do nothing. If the value of counter is more than 1, it will consume an item and decrease the value of counter by 1. It looks very simple, very straightforward. What is the problem then? The problem is increasing and decreasing a value of a variable is not one step actually. In machine language, this happens in 3 separated steps. First, you'll have your CPU register with the current value of the variable. Then you will increase the value in the register by 1 or decrease it by 1. Then you will swap the value back into the variable itself. So I'm going to نتكلم عن accumulation or subtraction, addition or subtraction. This happens in 3 separated steps. You will swap the value of the variable into the CPU register, increase the value of the CPU register, then store the new value of the item in the main memory. If the process was interrupted before the last step, that means before the new value, سواء كانت increasing or decreasing the value of the variable, before it was stored in the main memory, there will be actually 2 values for this variable. One of them is in the main memory, and the other is in the process control block. The process can be interrupted and swapped out of the CPU, and all the values of this process will be stored in its process control block. Next time this process will start execution, it won't go and read the value of the variable from the main memory. It will actually load the CPU register value back in the CPU register. So let us look at this scenario where the execution of counter can go like this. The producer executes register 1 equals counter. Basically, it was 5. Then the producer will execute register equals register plus 1. Now the value is 6. At this point, the producer was forced out of the CPU. The consumer was loaded into the CPU. For the consumer, it will read the value from the main memory, which is 5 because it was not changed yet. And it will consume an item and it will decrease the value of the counter by 1. Now counter for the consumer equals 4. Before it changes the value of the variable in the main memory, the consumer was forced out of the CPU. Now, we can see that the variable counter has actually 3 different values. 5 in the main memory, 6 in the producer's CDC, and 4 in the consumer's CDC. That's major inconsistency. This is what we call a race condition, where different processes are racing for changing a shared variable, a shared data entity. And this will lead us to the critical section problem.